Greetings everyone, I'm Bilkent University. I'm a senior electrical engineering student at Bilkent University. In this video, I'll be presenting my term project. It's a two-stage low noise amplifier, and I used key components in this project for the schematic and the layout, which makes use of gallium nitride technology. And our frequency band of interest is from 7.125 GHz to 7.875 GHz. Our center frequency is 7.5 GHz. And let me start by talking about the first iteration of my design, which is the one that I designed using lumped components, which actually does not include the Cree components here, except for the transistors, of course. And how I designed this, I actually opened two separate cells. In each, I placed the two different stages, the first stage and second stage, and designed them separately. I designed the input matching network, output matching network, and stability network for each stage, and then merge the two cells in a single schematic. Uh, I also needed to retune some things, but it actually came out. The results came out quite well. So, what were the tricks in this overall schematic? So, firstly, the since this is an LNA, and as we are using two stages in cascade, the first stage will dominate the noise figure of the entire design. And because of that, we need to use the stability network at the output side. Otherwise, the noise figure would be even higher. And since the second stage does not actually contribute much to the noise figure, we could use this stage to boost up our overall gain. So this stage will be used for increasing the gain, and this stage will be used for uh, uh, holding the noise figure at a relatively low level. And let me show you the results for this simulation. We used S parameter simulation, and you can see the results for that, the input and output reflections, the gain and the noise figure, as well as the stability factor. As you can see, it's unconditional stable, and our input and output matching values are relatively good. We get good isolation from these, and uh, here you can see the gain, which is relatively flat. It's actually has a variation of approximately a point 0.5 decibels, something like that, and we get a gain of approximately 27 decibels at the our frequency band of interest, and we have a noise figure of 3 decibels in this configuration. So what was the next step? It was to change the lumped components to transmission lines. But firstly, I actually changed the lumped components to lossless transmission lines, the built-in ones of ADS, so that I can change those ones to the lossy transmission lines of the Cree Foundry. So let me show you the one with the lossy transmission lines. The other one, I designed the other one using iterative steps. I replaced, for instance, the input matching network with a short stop connected in series with a transmission line, and I retuned that. I tuned that so that we can get the same characteristics we got with the lump components of the input matching network, while we are keeping all the other components of the entire schematic, so that we can actually tune the values according to our previous design. And I did that step by step for every matching network. Then we actually mimicked the entire design. So For transforming the lossless transmission lines into lossy ones, we use the line calc tool of ADS and use the Foundry information to the information we got from Foundry at the line calc, so that we can mimic the lossless transmission line. We can mimic the characteristics of lossless transmission lines with lossy transmission lines. You can see those the third iteration of our schematic here. The first one being lumped component, using lumped components. The second one using lossless transmission lines, and the third one being using the lossy transmission lines. And as you can see, we changed most of our lumped components, but we didn't change the ones we used for stability networks and bypass capacitors, as you can see here, or I don't know, DC feed, DC block. For those ones, we use again lumped components. But you can see these are not Cree components right now. We actually change those as well in the next iteration, which will be the one that I will show you next. So this was actually enough for me to get a good representation of the schematic before starting to the layout. So the layout is a bit tricky because these connections you see here do not come free. You need to actually have a line there, a physical line, so that you can connect this transmission line to the transistor and to the DC block. So that line is again in the form of transmission lines or steps, or I don't know. For junctions, you can use T junctions, or I don't know. You can actually use other components to manipulate the transmission line, so that actually you can fit the thing to actually smaller areas. So that's what we did in the next iteration. So let me open the workspace for the next part. So, oh, this is not this one. Yeah, this one. Okay. So yes, right. Okay. So here you can see the LNA with its symbol, and you can see our S parameter test bench. So let me push into hierarchy here to show you what the schematic will look like after you complete the design for the layout. So what we did here is to actually, I first changed the lumped components which were not which didn't belong to the Cree Foundry specifications with the Cree components, and after that I still did not have the connections between the components. As I said, you need transmission lines or other forms of material to connect every component in essence. So what I did was to actually open a layout and then use you can see here, place components from schematic to layout. I actually used this for the for all components in the previous schematic I have shown you. And for instance, let me open the layout view as well. For instance, I placed the first M line from the previous schematic, which approximately had a length of 4 millimeters or something like that. But if I actually put the entire thing like that, like if I had put the transmission line in a linear fashion, it would actually cost me a lot of undesired space. So as you can see, this is a relatively compact design. We have a height of 3 millimeters and a length of 7 millimeters. But if I were to not use this sort of manipulation of transmission line, then I would actually got a like linear transmission line with uh, 4 millimeters length, which would be higher than the overall length, overall height of the entire design. So that would be bad for making our design compact. So we needed to contain our space into uh, a relatively small area for all components, and we managed that by actually uh, using curves and junctions, and actually using curves was very beneficial in that case, because most of our components are transmission lines. You can see here we have transmission lines. There's a huge transmission line here, and again we have transmission lines. So you understand what I'm saying. You need to actually use curves and other forms of manipulation so that your transmission lines would be more compact. And as I said, we use other forms of connection as well. You can see a T junction here between the transistor and the capacitor. We also use the transmission line here also, so that we can connect the capacitor to the T junction. So we need every form of connection that we can use. We also use steps to connect transmission lines or components of different widths to each other. A good example would be the first component we place here. You can see a step. This is a greater width compared to this transmission line, so we use the step there to actually connect the two. Uh, and now let me show you the results of this layout. Uh, Alright, so no, is this the one? Yeah, this is the one. Okay. So this is our results. As you can see, let me first show you the gain. Our gain has dropped significantly from 27 dB to 21 dB, but that can be explained with you like initially we were using lossless components, but now all of our components are lossy. So this would actually have a great effect on our results, and it's visible here. So let me also show you the matching parts, the S11 and S22. So we actually improved upon S11 and S22 in our final iteration. So because I did, as I said, made the design iteratively also in the layout view. So I actually retuned everything so that while keeping other components the same, I retuned the component I was placing, and as I said, for space manipulation, I used curves or other stuff. And while I'm putting those to the layout, I actually tuned those values so that I would get better results. We actually got better results. And you can see the noise figure as well. It's again in the 9 dB band. There's no improvement or I don't know, decrease here from the previous iteration. Our stability factor is again higher than 1, so we made an unconditionally stable amplifier in our frequencies of interest, and which is from 10 megahertz to 8 gigahertz. And now let me show you, and as you can see, our OIP3 plot is left blank because we don't have the harmonic balance simulation in our schematic. I did that separately, but we changed that to S parameter. So I actually prepared a report for that. Let me show you the plot from there. You can see the harmonic balance simulations result here for OIP3, which is generally a good metric for linearity of our amplifier. And you can, as you can see, up to 10 decibels or so, we got actually a considerably good OIP3, which is about 46 decibels. and we use two tones for this simulation, uh, which are relatively close to each other, 7.49 gigahertz and 7.51 gigahertz, which deviate from the center frequency of our design by 0.01 gigahertz. And actually, this was all from me, from my design. You can see also the entire schematic here and the layout in another fashion. And thank you for listening, and thank you for paying attention. I hope you'll have a nice day.